Welcome to the cozy room, MPC cozy room. We have some jazz music in the background. Lounge. Hello. Hi, everybody. Thanks for joining us here in this cozy room for the session on model predictive control. We're going to present 4 projects in CalFlex Sub that use this technique to control different systems. Next slide. Uh-oh. That's not the slide that should be there. Nope. No, I think that the deck is wrong. 1 second. Can I share screen? Oh, you don't see that. Multiple panelists can share together. Oh, webinar.
Recording in progress.
Oh, yeah. That's why you couldn't hear me. How about that? Yeah, only the first 2. All right. Well, technical problem, but so we're talking about model predictive control. So for the 2 people in the audience who don't know what MPC is this control approach that uses models, typically of control system like HVAC or domestic hot water or lighting or many other things. In this case, it's mostly HVAC. It's predictive, so anticipates future events and plan how to react to them to optimize an objective function. The objective function could be carbon emission minimization, or it could be cost minimization or other things. And most of these strategies are supervisory control strategies. So I put the graph here because I think it's important to understand that MPC in this case is sending set points to a lower level controller, which is represented here as a thermostat. And the controller controls the HVAC unit sending direct commands to the components. So the compressor, the valves, and the other small components. So MPC can typically run every 10, 15 minutes and optimize this higher level objectives, and the lower level controller really controls the fine tuning of the equipment. We can see in the other slide here that we have a different type of systems that we're going to present here that span in different groups of appliances in different sector of the market. So in terms of standardization, there's more standardized and unitized systems in residential and small commercial, and obviously those are smaller, so they have smaller saving opportunities per system. On the other side, we go to larger commercial buildings and to district system. These 4 projects will show one of each case in sequence from the smallest to the largest. And we can start. Keaton?
Thank you, Marco. Hello, everybody. My name is Keaton Mand, and I'm a staff researcher at the UC Davis Western Cooling Efficiency Center. And today I'm going to give you a little highlight about the project that we're working on under CalFlex Hub, which is we call the dynamic heat pump for residential space heat and domestic hot water. So similar to what Marco just described, what we're working on is a supervisory MPC control that can be used on residential heat pumps. Within this CalFlex Hub project, we're using the same control system with a few modifications to control individually control multi-splits and heat pump hot water heaters. Within our MPC, we're using multi-objective optimization to optimize for both price and carbon emissions. And as I'd mentioned about the individual control, the way that we're building the supervisory MPC is we're taking a modular approach to try and de-risk the model or de-risk model predictive control to make it easier for this technology to get it into the residential marketplace. Next slide, please. So for our communication architecture, it's kind of broken into 2 parts here. One I call the data model framework. The part in the middle there, that's really where the MPC lives. So in our data model framework, this is where all of our data management is happening. This is what's getting the CalFlex Hub signal. We're also getting Midas, and we're also independently querying watt time servers. We're configured right now just to poll every 5 minutes based off of our every time that our MPC is updating, but that's a configurable parameter. Downstream or not downstream, in addition to the data model framework, we have our MPC, and there are 2 components because our MPC itself has no persistence. It has no memory. It starts up, generates the optimization problem, solves it, returns the solution, and then kills itself. We're doing this for kind of data portability and scalability reasons. But the way that we're doing this is we're building a methodology into the MPC that you can represent the underlying system that it's being controlled as a directed graph. And in that directed graph, the nodes are actual physical components of the system, and the edges show the relationship of how information flows. So what you can see here is I've highlighted the system graph for our heat pump hot water system. So you can see that we have a heat pump, a resistive heating element because it's a hybrid system, and a storage tank. So switching this from the multi-split to the heat pump hot water heater, the main component that is changing is the system graph. It would be replaced with something that represents the multi-split. Next slide, please. So what I wanted to share with you today is a little bit of a snapshot of some of the results that we've gotten so far in our simulations. What these simulations are really looking to do is to look at the interplay between the storage capacity of the hot water tank, the dynamic pricing from CalFlex Hub, and the timing of actual hot water use. So as you probably saw on the first slide, we have a couple of field sites. So the data that we've been using in these simulations comes from actual usage from the same 65-gallon systems, and a couple different, it's either a 1-bedroom or a 2-bedroom apartment. But in this result here that I wanted to show, the way that we did this analysis is we took this water flow profile and we basically rolled it in time to understand how usage and the dynamic price impacts your ability to do load flexibility. And what you're seeing here in the graphs is actually just a 1 hour shift. So you can't see much in the top two graphs. They're really the same profile. It's just been shifted 1 hour. But what you end up getting is a drastically different performance in a rule-based controller. Because in the first case on the left, you're seeing that the MPC uses about twice as much energy for twice as much cost, but there's no comfort penalty. And in this case, comfort penalty is just a monetary value that we assign to when there's no hot water in the tank. But if you shift the profile by an hour, the MPC performed almost identically, with the rule-based controller used far more energy, or used more energy but cost more because it used it at the higher expensive times. So what I was trying to highlight with this is that the baseline for comparing MPC is a little bit challenging because rule-based controls right now can't account for things like comfort, and occasionally they can just get lucky by being having no knowledge of these outside signals that we also want to optimize based off of. So because we don't currently charge for comfort, it makes it hard to kind of equate the two at that time. Okay, last slide. Yes, thank you. So from this so far, our key learnings is that hot water use has a big impact on load flexibility. Storage in the tank can help you shift an hour or two, but that might be not enough if your true goal is to have zero on peak runtime. Kind of this next point is leading into next steps, which we're right about to start our lab testing. So in our development, we are continually relearning that APIs and internet connections are not perfect. So in the design of this MPC, we had to make sure that we had the ability to operate with independent or incomplete information. And we're still actively researching about where our confidence in our state estimation fails. And the last piece was the thing I was really highlighting on the last slide, which is loss of comfort is not captured in bill cost comparison. So in terms of load flexibility, it's sometimes hard to have the complete picture of what MPC can do when we don't truly charge for comfort violations with RBC. Next slide.
Thanks, Keaton. Yeah, one very good observation. This same problem came up in other projects in the deployment projects, where when you have hot water and the profile changes, it's very hard to have a baseline. So, but especially with continuously very varying prices. So, very good point there. I want to also mention, I forgot at the beginning, that these are sort of R&D projects. So you'll see a lot of like open question and a lot of challenges in implementing that, but also a lot of opportunities, because this is really the only way you can, optimize for variable prices that continuously change. So the next one in our team is
Hello everyone. Thank you for having me here. And my name is Sang-Woo Ham. I'm a postdoc researcher in ABNL. Can you go back to the previous slide? Yep. Yeah, so today I'm going to introduce our work on dynamic heat pump design and control for small commercial buildings. Actually, we can cover medium buildings as well. So we are designing a MPC to be used for real world situation, especially we don't have enough sensors and infrastructure. So mainly targeting thermostat and package system. The main target is to reduce the peak demand, also carbon emission, and if there's dual fuel system, then natural gas usage. We are testing our technology in our Flex Lab and one site in the New York, and now we are actively working on several sites in California. Can you go to next slide? Okay, as I said, we proposed our technology and we tested on Flex Lab, and then we tested in the winter 3 months in commercial building in New York, and now we are working on VRF system in UC Davis. In terms of the communication, our technology is targeting two types. One is OEM cloud, and the other one is local network. So basically, any small, medium commercial building, they have their own Wi-Fi connected thermostat or thermostat with some local network such as BACnet. And we design our middleware to be connected with flexible to various clouds and BACnet system. And that middleware also get the price signal from CarFlexor. Can you go to the next slide? So here are the results. The first top part is the FlexLab test, and you can see the gray area is the peak time. And when the price is high, there is like money hitting demand. And the MPC is mainly just shifting that morning peak to the earlier morning. One thing we want to emphasize here is this one only is a single space with RTU and on thermostat. And we tested two types of MPC. One is MPC with several sensors like supplier temperature, internal heat gains, and the other one is just thermostat and RTU. So they have similar performance, and we are actually confident and that technology is applied to one building, small building in New York. The building has like 5 municipal heat pump and 1 gas furnace. And actually there is 1 gas furnace, but they retrofit 5 heat pump for electrification. But still their control is a little messed up. They are used without any coordination. And MPC is trying to reduce the natural gas usage while coordinating heat pumps to reduce peak demand. And the result is just shifting the morning peak demand to the earlier morning time, and also completely eliminating natural gas usage. Can you go to the next slide? So here are key learnings. We design a MPC that can be used small, medium commercial building without a major sensor retrofit, and that shows very good performance. And then we tested on that MPC to rear building. We can also find out we can extend our application to the other systems such as dual fuel system to reduce the auxiliary heating or natural gas heating. And finally, one thing we found out is several mini split or some thermostat doesn't have good API connection, so that is major hurdle for us. We need more labor for engineering effort, so that interoperability is still very challenging for real world implementation. So hopefully we can also solve it, see more that solve the issue.
Thank you, Sang-Hoo. So as you can see, we are going from residential now light commercial. Similar challenges and APIs are being mentioned already twice, and then we're moving to large commercial buildings.
Thanks, Marco. Good afternoon, everyone. My name is Ettore Zanetti, and I'm a postdoc here at the lab. And if you can go to the next slide. So in this part of the presentation, I'm going to show you the field test results for an MPC applied to a large commercial building here on campus, actually. And in particular, we were controlling the office space of the building, which consists of 2 floors of the building. And the HVAC system for this building was made up of an underfloor air distribution system, then is connected to 4 rooftop units. And the MPC is a supervisory controller, as Marco mentioned before, where it controls the fan speed set point and the air supply set point for each of the RTUs independently. If you can go to the next slide, please. And in terms of communication infrastructure, the core of the MPC is a server in building 90, another building within the campus network that takes price signals that are used for the optimization and weather forecasts. And then it takes also monitoring data from the building automation system and from different sensors that were placed ad hoc inside the building to better operate the MPC. Then it runs the calculations, and all the results and data are stored in a separate database in another LBNL server within the campus. Then these set points are sent back to the building for active control. If you can go to the next slide, thank you. So here I'm just showing you the results of one of the field tests where basically they were conducted in summer from early July to the end of August. And the MPC was turned on for the last week of August. On the x-axis, you have the hours of the day. And on the right axis instead, you have the dynamic electricity price for the summer that we used from our partners within the project. And you can see that the peak of the price is within 6 and 8 p.m. as we can expect. And then on the left axis instead, we have the hourly energy consumption, electricity consumption of the HVAC system in the building. In green is the MPC, and in red is the default operation of the building. And you can see that by doing a lot of pre-cooling, the building is actually able to shift the load during the peak hours by up to 50%. In fact, if you can look at the next slide, and in particular the plot on your left, which is very similar, is the same kind of box plot for the same period, but in this case, we are looking at the temperature distribution in one of the zones. You can see that the MPC during the early hours of the morning actually lowers the temperature in the building with respect to the default operation. However, you can also see that in general, the MPC is able to keep an overall tighter boundary on the temperature with respect to the default controller. So even though it's lowering the temperature, comfort is not really affected, and we have no complaints from the users. So what does it mean from a cost perspective? Well, if you look at the whole testing period that we did from July to mid-October, in the chart on the right, you can see that on the x-axis, we have different external conditions, in particular, the external air temperature. And on the y-axis, we have the daily cost of running the HVAC system for that specific condition. Again, in red is the MPC off, and in purple, the MPC on. And you can see that the MPC on average is able to save 40 to 50% of the running costs. So it's an encouraging result. And then finally, if you can go to the next slide. So what can we take home from this? Well, the MPC can shift the load, as me and my colleagues have shown. However, this makes data management much more critical. And going a little bit more in detail, the MPC was able to, during our field test, to shift the load using different dynamic prices, one for summer and one for fall. And it will probably be able to optimize for any dynamic prices that is reasonable using the same code. So that's one of the advantages with respect to like a custom implementation of a rule-based controller. Thermal comfort was not compromised. And if anything, actually, the MPC was able to keep a tighter boundary on the temperature. However, running the MPC required a continuous effort in trying to deal with data stream interruptions, server restarts, software updates, and like a whole sort of like issues that are usually not talked about. And furthermore, because this is a supervisory controller, it relies on knowing what's the underlying control logic is. And in our case, during one of the tests, there were wildfires around here, and the facility operator shut off completely the outside air intake, which the MPC uses. And so the consumption of the MPC was actually much higher than what we expected. So we have to address that. In conclusion, I think that it is definitely a viable technology, but in order to scale it up and spread it, there is need for more investment and research. Thank you all.
Thank you, Ettore. And as you can see, as the building grows larger, the problems grow also in size. Last but not least, Dong-Hoon.
Hello, everyone. I'm Dong-Hoon Kim, research scientist at Berkeley Lab. Would you please go to the next slide? So this is our final slide. So long journey, finally. The scale in this system is totally different. In this case, we are looking for a district energy system. It has huge chillers and PVs, and especially summer energy storage. So basically the goal is how to operate this huge system, megawatt scale in terms of power and tens of megawatt hour in terms of load shifting capability. How can operate those systems in response to a grid signal for the cleaner environment. This demonstration project has been worked with the UC Merced, and the picture shows the system of the chiller plant, and the circular things shows the chilled water tank. The height is around 30 feet and diameter is 30 feet, which can contain 2 million gallons of water. So you can imagine that how much energy can be stored, charged, or discharged in this summer energy storage. Next slide, please. We propose, because of some complexity over there, especially the dynamic price signal, and also, as I shown before, it has a huge solar farm over there, is 5 megawatt scale. Typically, renewable energy on-site generation is smooth, but not always true. Sometimes cloud day, the solar generation reduced a lot within a very short time period. So we proposed, instead of a rule-based control, we proposed model-predictive control, and the right-hand side shows the way of implementing the MPC. Just a quick summary, we are reading the weather forecast data from a weather station, and using that information, we forecast the chiller plant campus cooling load, and also we are utilizing so-called PV library to forecast what's the on-site PV generation, and also getting a dynamic grid signal, in our case, Carflex of signal. And using that information, optimizer try to, based on some model built in, optimizer try to find out what's the best way in order to minimize, in our case, utility cost, including the peak demand charge, which is very significant in our campus case. The left-hand side shows a little bit more detail of HVAC plant configuration. Next slide, please. This is a quick summary of our experimental result we have been performed. And the first subfigure shows that the price signal we are receiving is a 4-day. And the shaded, gray shaded area is when the price is high, just to simplifying our analysis. And the second subfigure shows the power measurement, and also the third one is the state of charge within the chilled water tank. So 100% means fully charged, and it is bounded in our case, in this case, around 40%. So basically, cold water is 40% to up to the 100%, depending on the model predictive control. And the last figure shows the chiller load and the campus load. One thing that there are a couple of things that I wanted to emphasize, but the major message, two major message is when the electric price is high, is it try to shut down all the chillers as expected, and also the renewable. If we look at the power signals, is a campus net consumption. Renewable on-site renewable generates around 4 megawatt, but we are, by using the model predictive control, the net power consumption is always positive. That means the 100% on-site renewable energy generated has been self-consumed. And the right-hand side, we repeated this experiment and collected some of the historical data to compare what's the benefit. The right-hand side shows the representative daily averaged the load for campus net power consumption profile. The red one is before the MPC. The blue one is after the MPC. You can see the net power consumption for the conventional case is typically goes to around 2 megawatt. That means on-site renewable generated is basically going back to the grid, but after running the MPC, we almost almost 100% eliminate this excess on-site generation, and also smoothing this the load curve in the campus. Next slide, please. There's some animation. Yep, just skip. I want to kind of summarize the key learnings. I think a couple of them are pretty clear, but two things that I wanted to emphasize is, especially for the large commercial building or district energy system, revising building management system in favor of advanced control is really challenging because their building management system, their control sequence is like if we change one and that affects to the other and the other subsequently, and facility operators are very conservative, and if we ask them to change one logic in their energy management system, they have to test whether the modified sequence is okay or not. So you can imagine that how challenging revising EMS logic in favor of advanced control. And another important thing is liability. So if our system, in our case, is typically the utility bill over there is around $100,000 per month. So they really care about their financial impact. So especially if something goes wrong, then who are gonna be responsible for? So those are really challenging part that I spend a lot of time to make them convinced. But that is, we don't have the perfect solution yet. No clear idea, rather than just iterating and keep monitoring what's going on during the MPC implementation. And one thing I also wanted to emphasize is not just for all the model predictive control, in our case, another challenge is people always wanted to know what's the value proposition of these technologies, but that's really challenging part that has to be addressed. Okay, so that's all of my presentation.
Thank you, Dong-Hoon. An applause to all the panelists. Yeah, thanks again. I just want to kind of follow up with Dong-Hoon saying that I didn't say this at the beginning, but in addition to HVAC, you also have PVs, and you could have other end users, and MPC kind of can control them all in like in an optimized way. Okay, I think we're at Q&A. Do we have a candidate question from over there? Okay.
Run this back and forth. Yeah, hi, thank you, everyone. I have a few questions so far, but please feel free to enter additional ones as we go through these. So question one, model predictive control commonly requires a model for the system from residential scale buildings to commercial scale buildings. How are the models obtained in these different projects showcased? And this is for anyone who wants to answer.
Yeah, I think it's each one has a different answer. So let's start with the first one.
So for our project, the water heating model, we're using a first principle model for the water dynamics within the tank, and then just a simple RC transfer for the tank shell and the other properties there. Through our lab testing and everything like that, we've been able to identify like the capacity that the heat pump actually puts out, as well as the electric resistance heat. So all of those parameters are put into our model. The way that we see this working as we go forward is that, like, yes, parts of the heat pump water heater change as you go to different manufacturers or different installs, different tank sizes. But what we have is kind of the core model. So you would make small iterations from that to account for larger tank size, bigger heat pump capacity, things like that. So it's the core where you can start from, and your predictors can even learn from. And on the space conditioning side, for the building, again, a simple RC node circuit. And then right now, we're putting together the performance curves for the multi-split system.
Can I go? Okay, sure. So for the large commercial building, for this project in particular, actually the model was already there because it was developed in a previous project. And if the person that has the question can send me an email, I'm more than happy to share the details of the papers where a lot of models were tested, but the models that are running now are, to be honest, fairly simple. Like, despite the fact that the building is really big, it just divided in 4 zones, and each zone is a simple gray box model with an RC network, because we realized that more complex model tend to be a little more accurate, but the data you use to calibrate them has to be very good. And so there is a trade-off between how complex is your model and how reliable is your model. And in our case, we do recursive training of the model once every week. And then we just use the latest version of the model so that any changes in the control logic, the seasonality is accounted for in the model. And it's been behaving pretty well from that point of view.
My application is our application is small and medium commercial buildings, and I emphasize that we are not trying to use a lot of sensor data. So the first thing we want to do is capturing the physical characteristics, so that we use simple gray box or RC network model for linear building system. And also because of the simplicity, so one might criticize the model is not very inaccurate, but that MPC is designed to be handle robust toward that situation. So capturing some physical characteristics and the other missing part is, if significant, can be captured by other black box model, which I'd say hybrid approach. But if not, then we can just go with the gray box model, and the MPCs like disturbance rejection algorithm can keep updating the state current situation, so that we can at least guarantee the MPC's performance in short-term peak demand coordination, etc. It's very light and scalable modeling. And one other thing is we are actually trying to make some metadata, which is a flow area and window exists or not. Those information is parsed as JSON or brick, and then we just automatically convert it to our system, the model identification process, which is pretty much generalized nowadays. So we are kind of competent on that part. But
I think I can spend like 30 minutes to discuss about it. Yeah, but one thing that I wanted to emphasize is modeling is really one of the biggest kind of a research question, because just historically, when I first started learning the MPC applied to the building like 15 years ago, there's still conversation which model is the best suitable for building applications. It's like it lasts 2 decades. And when I talk with chemical process engineers, which where the area originally not originally, but extensively developed the theories and applied to the field, they are still arguing which model structure is good or not. So I can say one thing, but although it's very diverse and depending on our application and the model structure is really depending on also really depending what's available sensors and the actuator, because the control is basically the sensor and actuator. That model means in between the sensor and actuator. So depending on the sensor and motor structures, there are a variety of motor structure we can identify. But the important thing that I wanted to emphasize is there should be some balance between the accuracy and the optimization friendly formulation. We don't want to make very complex model which could make mixed integer nonlinear programming which may not be applicable for real-time MPCs.
And that's a lot of math. Next one. Thank you, everybody.
Yeah, so question number 2, do the MPC predictions take into account cloudy sky or is it clear sky? And does it matter?
I think this is specifically relevant for PVs.
We utilize some of the open source library that basically gives a forecast based on some of the physical information of on-site PVs. It predicts what's the on-site power renewables generated. Unfortunately, especially when basically based on when there's a sunny day, then accuracy is very, very great. I think that's obvious. But when it goes to the cloudy case, it is really challenging. The accuracy is not that great. We tested this accuracy with some historical data and real-time pulling of the forecast, but it's not that great. That I think is important research topic to how to improve the accuracy for the cloudy cases. Well, one thing that I wanted to add, California is a good place because it's not compared to the New York, because it's not very cloudy every day.
Sounds good. The MPC is gonna grow in California because of that. Next one.
All right, next question here. What are the technical challenges in developing these technologies? It's a good one.
For the next 5 hours, we're gonna cover this. So how about we do areas? Okay, so there's integration, I would say, which is dealing with everything you have to control or get data from. And there's modeling, which we discussed a little bit, but it gets even more complex when you start adding additional pieces and components. I think labor and what we call the PhD in the loop is one of the other challenges, that when you disconnect the PhD, the model seems not to work anymore. Any other thing that you guys want to discuss as sort of the last one being the training needed for set up the system?
To give you an extra challenge, we have 5 minutes.
5 minutes to solve MPC from TRL 5 to 9. Go.
Yeah, I think the best way is I will just forward the couple of literature review we have done at the LBNL, because as Marco mentioned, we can discuss about it for 5 hours about what's the technical challenges over there. But I may, yeah, there are too many things. I think the best way would be just sharing some literature.
I think they share most of the challenges. If I can be a little positive though, I started my PhD not that long ago, 6 years. And back then, actually, there were like 6 papers on field demonstration of MPC and like thousands of papers on theory. Well, I think now at least, even within this project, we can see that the technology is applied to real buildings. So there are a lot of challenges, but it's progressing, and for sure it's getting there.
Just quickly, MPC is a supervisory control, and some small, medium commercial building or residential case, the user can override the MPC. So there conflict of control, and that kind of like many unexpected situations happening in the real world implementation. So having that workflow, like handling missing data and those things are good. But as Marco mentioned, if the PhD left and that experience is going away, so that's another we really need to take care, make a like as a kind of solution. Yeah.
And just 1 second. I think there's we've been discussing sort of the next step and kind of what's the roadmap to bring this to market at scale. And I think one of the elements which is in the graph there is really bucketing the problems, because the on the low side you have systems that are fairly similar, so you can probably find generalization for those, and it's good because they need to be very inexpensive, the models to create. On the other side, the district system, they're so huge that you can get a PhD to actually do it. The middle range, which is is maybe the most challenging, because the buildings are kind of all different and like all snowflakes, and you don't have a lot of saving potential. So that's sort of one of the areas that is more. But there's work on the both the other two areas, and I think that we're getting closer.
Maybe I'm not answering the questions raised, but I wanted to add, looping in a PhD, I think is necessary. For example, when we develop a mobile phone, a lot of experts develop those smartphone, but from the user point of view, we are just using it. So I think the technology seems like, for example, medium or what we discussed from medium and large commercial, if researchers really develop and come up with a very good solution, at least applicable for similar type building system, then including the PhD or expert, I think is a necessary component. But definitely we don't want to include the PhD for every single different buildings.
Thank you. I think that we should probably join the other group and finish up. Thanks everybody for joining, and thanks to the panel participants to present. Bye.